Hello, everyone. Thank you for joining us at PowerAmerica's monthly technical webinar. My name is Rogelio Sullivan, and our speaker today is Dr. Akin Akturk from CoolCAD Technologies. We have these webinars every first Wednesday of the month at 12 o'clock noon, and we welcome the entire wide bandgap community to join. And each month we have a different speaker, normally from one of our member universities, but we've begun to open up the webinar opportunity to a lot of the small businesses in PowerAmerica, and CoolCAD will be the first to present today. Next month, on December 5th, the webinar will be given by Ranbir Singh of Genesis, and we hope that you'll join us again in a month from now. But today, I'd like to introduce Dr. Akin Akturk. Akin is the co-founder and vice president of CoolCAD Electronics, LLC, located in College Park, Maryland. He's also part of the research faculty at the University of Maryland, College Park. He earned his PhD in 2006 from the University of Maryland and was also awarded his MS degree in 2001 at the University of Maryland. He's published more than 100 scientific papers on silicon carbide and silicon materials, device and reliability properties. His research interests include electrical and optical measurements of silicon carbide sensors, especially those designed, laid out, and fabricated at CoolCAD. His research interests also include electrical and reliability measurements and compact and distributed electrical and thermal modeling of SiC power devices. As part of his terrestrial and space reliability measurements, Dr. Akturk regularly performs radiation tests for quantifying failure in time curves and safe operating areas for these devices in various applications. In addition to his work on wide bandgap devices, Dr. Akturk has done extensive compact and distributed modeling for CMOS technologies operating at low temperatures. His analysis covers a wide temperature spectrum ranging from cryogenic temperatures to a couple of 100 degrees above room temperature. He participated in the design and investigation of three-dimensional heterogeneous integration technologies, where he mainly focused on self-heating effects. Along with his colleagues, he was awarded a patent for heat removal by the U.S. Patent Office for this work. With that introduction, I'd like to introduce Dr. Akin Akturk.
Thank you very much for the introduction, Rogelio. And today we're going to talk about natural background radiation and its effects on power switches, and especially silicon carbide power switches. So the title of the talk is Quantifying Power Device Reliability Due to Terrestrial Radiation, which is the natural background radiation we all live with and we should deal with its consequences. So, as Rogelio said, my name is Akin Akturk. I'm with CoolCAD Electronics. It is a small company located in College Park, Maryland. It's a spin-off from the University of Maryland. And you can see some of my colleagues, Neil Goldsman, Jim McCarty, Zeynep Dili, Mitchell Gross, and Asana Abate. Now I'm going to the second slide. So the purpose of the talk is to introduce the natural background radiation to you and hopefully explain how it affects power device operation and how it affects power systems and the reliability in power systems. So I'll start with the introduction where this radiation comes from, and after that I'll describe how it affects the power systems. So the terrestrial neutrons and very high energy protons can reach sea level, and there are more of them in higher altitudes, and they affect power device, especially power device operation. They also affect other computer chips, and in those ones it causes upsets, and in power device it causes failures. And then we'll discuss how silicon carbide power devices fare against this type of radiation, and how to mitigate power device failures against this. And lastly, we'll compare some silicon carbide devices with silicon devices and show how silicon carbide fares. So next, this is the same thing I just talked about. So we'll start with explaining the origin of terrestrial neutrons, which is the main background radiation that's important for power switches or any microelectronics. And then we'll talk about how these neutrons cause failures in silicon carbide power devices. And I'll briefly explain how we perform these experiments. So we literally measure failures and calculate failure rates using these measurements. And then I'll show some of our measurements and some of our failure in time curves, calculated failure in time curves for power devices that are commercially available right now. And we'll compare silicon with silicon carbide, and I'll briefly explain the physical mechanism leading to failures in silicon carbide power devices. So, what is this terrestrial neutron radiation? This is a busy slide, but let's first focus on the top right. As you can see, in space, you have very high energy protons, electrons. In addition to those, you have heavy X-rays and gamma rays and heavy ions. So, and as you can also see, there's no neutrons in space. So where are they coming from? When the high energy especially when the high energy protons hit gases in the upper atmosphere, they cause a nuclear reaction. And one of the byproducts of this reaction is neutrons. In addition to neutrons, you also have muons, pions, and electromagnetic waves and charged particles. But the important thing about neutrons is, first of all, they are heavy, so they can, compared to muons and pions, so they can do more damage. And the second important thing is they do not have charge. So they can go through the atmosphere without being deflected by the Earth's magnetic field. Compared to neutrons, other charged particles that are produced as a result of these collisions, they are being deflected and so removed from most of the atmosphere. So neutrons can reach all the way down to the sea level in large quantities, and can cause upset power switches. So you can see some of the neutron flux numbers in that figure. So the neutron flux usually reaches peak value at around 60 or 65,000 feet. It's about 20 kilometers altitude. And it drops roughly an order of magnitude when the altitude is half of this, at 30,000 feet. And at ground level, it drops by another roughly 2 orders of magnitude. So at sea level, you have high energy neutrons with a flux of roughly 0.001 neutrons per centimeter square per second. So these are very high energy neutrons, and they can cause upsets. On the left, you can see what's in the natural background radiation. So the x-axis is atmospheric depth, which is correlated to the altitude. And on the y-axis, you can see the flux per centimeter square per second. And as you can see, there are lots of neutrons at high altitudes. And at the ground level, actually, you have more muons, but they do not cause, they cause minimal amount of failures in power device. They can also cause failure, but since they are much lighter and they do not interact much, their failure rates are lower. And in silicon devices, they are more associated with causing failures at low biases. And for mid to high range biases, neutrons cause the failures in silicon. So this is a background radiation, and we must all live with. And depending on your altitude, latitude, or longitude, you may get a different neutron flux. And depending on the day of the year, there will be also a different neutron flux. In solar events, you get more of these particles because there will be more cosmic rays. So how do neutrons cause failure? So neutrons themselves do not interact with the material. So they'll just go through the material without ionizing anything because they do not have charge. So the only way they cause high energy neutrons cause damage is when they have a head-on collision with one of the lattice atoms. Since neutrons have high energies and appreciable mass, they can dislodge one of these lattice atoms. And a dislodged atom can is very effective in depositing energy into the device. It will create electron hole pairs and that will create a short when the device is in off state. And that short can cause a catastrophic failure in the form of a burnout or a gate rupture, which I'll describe later. In addition to the primary knock-ons, you can also have secondary knock-ons, or you can have nuclear reactions and the original atom converting into some other element. So in silicon carbide, we have silicon and carbon. And in the upper layers, we may have some oxygen and aluminum or other things. So when a neutron goes into the silicon carbide power device, it's most likely to hit a silicon or a carbon atom. And the figure on the left, the top part shows what kind of energy ranges that can create as far as primary knock-ons are concerned. Since neutrons are a result of lots of collisions with atmospheric gases and the high energy cosmic rays, they have a spectrum. So the atmospheric neutron radiation energies can go from less than an MeV to up to a GeV, and at high energies you can find less neutrons with high energies, so you have more of them at lower energy. So this is a spectrum of energies. The knock-ons will also have a spectrum of energies. So that's why you can see at low energies, recoil energies are low, and at high energies, since there are not too many neutrons, your yield is again low. So there's an optimum point. In silicon, you can see it's roughly 1 MeV, and in carbon, you get a peak yield around maybe like few MeVs. But you also have some silicon and carbon primary knock-ons with higher energies as well. And you can have aluminum and magnesium. Aluminum can come from the interconnects, or also those two things can also come from nuclear reactions with lattice atoms. And on the right, you can see how far this primary knock-ons can travel within a silicon carbide device. On the green curves show that if you have a silicon knock-on, it may travel with, I believe it's like 15 MeV energy. It can travel up to 6 microns within silicon carbide. And if it's a carbon knock-on, it can travel up to 10 microns within silicon carbide. But for a knock-on to cause a power device failure, it doesn't need to travel the whole length of the epi layer or the drift layer. It can travel part of this drift layer and can still cause a failure, which is mostly the case for silicon devices. So to perform the test, you can either go at a very high altitude and use many samples and test them in long periods of time, or you can go to the only Terrestrial neutron simulator that's available in the US, and that's located at Los Alamos National Lab at the Los Alamos Neutron Science Center, or LANCE. And this center has 2 beam outputs that simulate the terrestrial neutron background radiation. On the right, you can see how it matches with the atmospheric neutrons. At this place, you can have neutrons up to 600 MeV energy. So beyond that, there's a cutoff. And the lens neutron source is the best in the world, and there aren't too many of these sources because it's really hard to stimulate very high energy neutrons and also achieve a spectrum that's similar to the atmospheric neutron spectrum. So how did we do the test? On the top left, you can see a circular beam output. So the beam output is actually behind this circular cylinder, and it is generated by high energy protons hitting a tungsten target, and that creates neutrons among other things, and the other things are filtered out. Then neutrons travel either roughly 10 or 12 feet and come out of a hole in the wall, and is one of them. And then they go through a neutron counter that shows how many neutrons are coming out. Then we put our devices in the path of these neutrons, and the biggest collimated output of this source is about 3 inches in diameter, and you can fit up to 6 devices within 3 inches. You can also stack them back to back, but as you stack more of them, you lose some of the neutron spectrum because of the scattering by the first and the consecutive stages. So it is better to put one set of devices within the direct range of these neutrons. And on the next to this beam output, you can see how uniform the beam output is. That's specified by that blue area, and how 6 devices can fit into this irradiated area. And you can also see our circuit. What we do is during the whole experiment, you monitor the drain voltage on the device. The gate bias is shorted, gate is shorted to source, and most of the time you increase the drain bias. So it's in blocking state. And then we continuously monitor the drain bias during the whole length of the experiment. And when the device fails, you lose the drain bias goes to 0, as you can see on the right. And then we also record the number of neutrons that cause that particular device to fail. And since there are 6 devices in this case, one fails, then you don't interrupt the experiment, and you wait until either a appreciable number of devices fail or a large enough fluency is reached. And once you have a statistics about which devices failed due to X amount of neutrons, then you can calculate the failure rate curve or failure cross sections, and you can use them to calculate failure in time curves, which I'll explain a bit later. So what happens when a device fails? As you can see, when a device fails, as you can see at the bottom, when a device fails, the drain bias goes from a very high value to 0. And for this plot at the bottom, the Y scale shows a scaled down version of the drain bias. So I believe when it says 2 here, it corresponds to about 1200 volts. So you can calculate the scaling factor. So as soon as a device fails, you lose the drain bias, and if drain shorts the gate or source or both. And in most cases, drain shorts the both terminals, and all terminals short to each other, or all terminals short to each other. And you can see the damage on the die most of the time with your clear eyes and with your eyes if the part is deleted or open. And you can see few examples here. As you can see, there a hole forms, and it's generally about a millimeter in diameter, so it is clearly visible. and from that point on, device catastrophically fails. When this forms, device catastrophically fails and becomes useless. So we have a paper on this. You can get more information about this by checking this paper out. So after we measure failure cross sections, so that is to measure it, we write down when a device, how many neutrons it takes to fail a device within a set of devices, and we either wait enough number of devices fail or a large fluence, neutron fluence is reached. A large neutron fluence means in the actual application, it would take a very long time to reach that level. So then, using those data points, we calculate failure in time curves. And failure in time is defined as the failure in 1 billion device hours. So if you have a hit rate of 1, you'll have 1 device fail on average every billion hours. Billion hours sounds like a lot of hours, but if you have an application with that requires deployment of many of these devices, then it can become a very short time period. So one such application is like automobiles. So if in a car, if you need to use maybe like 20 of these power switches or 10 of these power switches, and you have about like 10 million cars, then your fit multiplies by 10 and also multiplies by 10 million. So it becomes 100 million. And if you have a fit of 1, then it means every 10 years you'll have one of these cars fail due to one of these power devices fail, unless you make a circuit that has some redundancy that compensates for it. So for large applications, this is a very important effect, and especially the automobile people do this test regularly, not just for power devices. They also do it for microcontrollers or other integrated circuits, because in those, the same background radiation causes upsets or glitches that can make a car fail. Or in the case of, for example, a driverless car, that glitch can cause a fatal accident. So they always characterize the failure in time curves for microprocessors, and the power people, they also use it to design power converters and switches that is not very likely to fail within the average useful lifetime of a car. So that target can be, the cars may be designed for 10 or maybe even more than 20 years, and you don't want any of your cars fail due to one of these power devices fail. So if you look at the plots, these show different silicon carbide power device failure in time curves as a function of bias. So if you go higher in bias, you're more likely to fail because the fields are high, and that can give rise to a catastrophic event easier. And here on the left, I show 4 curves for 4 different voltage rated parts. And on the right, I show that part that bit curves as a function of bias for 2 different silicon carbide devices. So the higher the voltage rating, it will start failing at a higher bias. And also, once the failure starts, as you increase bias, the failure rates will increase exponentially. That's the general rule of thumb. So this is a very busy picture, but the main takeaway point here is like we regularly test devices, silicon carbide devices or gallium nitride devices or silicon devices. We mostly test the silicon carbide devices. And then get these varying time curves and then convert them to using these varying time curves, use them in reliability analysis, and so that also the circuit designers can use them to design more resilient, terrestrial neutron resilient or terrestrial radiation resilient circuits, so they would not fail due to this effect. Just to remind you that as far as like microcontrollers or integrated circuits are concerned, in silicon, terrestrial neutron radiation is the biggest source of reliability concern. So that is a lot more important than any silicon MOSFET failing due to high field. So this is the main reliability concern in those devices. So it may be the case for silicon carbide too. So it needs to be characterized, and then the information needs to be used to design a circuit that would last many years in a large application. So on the right, I'll talk about more on this later, but on the right you can see that all different voltage rated parts, we measure different voltage rated parts and the different parts from different vendors, but there's a way to collect that information onto one curve. And we plotted this curve with Dan Lichtenwolder from Wolfspeed, and he did a great job. What we did was we plotted varying time normalized by area versus applied bias normalized by the avalanche rating. So there's some trend irrespective of who makes these devices and what the voltage rating of these devices are. And so I'll talk more about this in the next few slides. And here I compare some silicon carbide power devices with some silicon power devices. This is a busy picture, but the main takeaway point is at high biases for the similar silicon and silicon carbide parts, silicon has much higher failure time values. So that means at high biases for the same kind of device, silicon part is much more likely to fail within a given time. And that is true as far as silicon power MOSFETs are concerned, and also silicon IGBTs are concerned. But as you can see on the right, if you go to lower voltages, sometimes there's a crossover point. And at low biases, silicon carbide MOSFETs are slightly more likely to fail compared to silicon power MOSFETs or IGBTs. But as you can see on the y-axis, at this point, the fit numbers are generally low. And so that turning into a real catastrophic failure event is not very likely, but that also depends on how many of these devices are deployed or used in an application. So at high biases, especially closer to the rated voltage, silicon almost always fails at a higher rate. But as you go down in bias for the same type of device, there tends to be a crossover point below which silicon carbide fails at a slightly higher level. But at that point, the failure rate is generally very low. So depending on the application, this may be okay, or the part needs to be derated. In silicon, what people do is like they generally derate the part so that a certain fit number is achieved per device. So when the system is deployed, your fit numbers are below, the total fit number is below a certain value. So in a small, medium applications, the total fit number can be about 1, but in a large application, it can be like 10 or 100. And also for aerospace applications, you want low fit numbers, so the lower the better. So you don't have any device failing or system failing due to one of these devices failing. So I briefly talked about this normalized silicon carbide power device failure rate. So this failure rate per area versus bias normalized by avalanche rating. So is this unique to, so the question is this unique to silicon carbide? And it is not. So the same thing is observed in silicon too. So irrespective of what kind of silicon power device you have, there is a way to convert that failure rate so that all failure rates collapse onto one curve. And this was done back in the 90s by Zeller, who I think he used to be at ABB. He may still be there. And they did this silicon studies, and they get these curves to get a universal trend. So there's a similar trend in silicon carbide as well. So what we're doing right now is we also try to characterize it for silicon carbide so it can be used in calculations. I had one question, but actually it disappeared on the side of the screen. Maybe I'll answer it later. I cannot see the question anymore. So what we do is, like, once we characterize it, we can use these models in TCAD simulations and get a very zeroth order approximation of the failure in time curve for any hypothetical device. But this is a very rough estimate, so in general all devices need to be tested for this application. And then we can get exact numbers for a particular device, which is going to depend on how you design the device, and also it will depend on, so for example, if the device is a punch-through device or a non-punch-through device, you get different failure rates or bias-dependent curves. So we can simulate and get some zeroth order approximations using our first order estimates, and then measure them later on to see how well they match. And once we're confident about the failure rates, we can pass them to the circuit designer, and they can design a system with a particular fit number in mind for the entire system. So I'll quickly go through this because I'm almost out of time. So what's causing this failure? So when neutron knock-on create electron hole pairs along its track, it will create a short within the active part of the device, and that short can cause a power device failure. This is similar to heavy ion induced power device failures, and these tests are done for space applications as well. And that failure can be in the form of a burnout or a gate rupture. In the burnout case, you have a current flowing between the source and drain, and that's sustained for long enough, and in the meantime you have lots of joule heating within a very small area, which then causes lattice damage and shorts source and drain. In the gate rupture case, the electrons and holes created along the track of a knock-on, they are separated, and they pile up. One type of charge piles up under the gate, which causes gate field to increase beyond the safe operating field values, and that causes a gate rupture. So to find what kind of event causes failure in silicon carbide devices, we do transient tests. We try to capture the current bumps or that are a result of this primary knock-ons or secondary knock-ons, and that causes a failure. So on the right you can see so we have this circuit. Once the device shorts, all the charge within that capacitor, which is called the stiffening capacitor, is dumped onto the device under test, and you can get tons of current flowing through the device. once you see a lot of current flowing through a device, at that point the device is already failed. But if you zoom into the beginning of the failure, you can see there's a small current found that initiates this catastrophic failure. And using that information, we try to determine what's causing these failures. And then if we know this, the root cause of these failures, we can design the devices that are resilient to this type of radiation. So our initial preliminary data shows the failures are a result of some kind of burnout event. And what happens is, like, the primary Neutron creates lots of electron hole pairs along its trajectory. And it's about 1 square microns in area. So you have this track of electron hole pairs in a column. It's about 1 square microns, and it can be as long as several micrometers. And then you also have the high field because the device is in the off state. So because of this, you can have a loss of Joule heating within a very small volume or small area, the J.E kind of heating. And since this happens very quickly, it generally happens within few nanoseconds. You don't have time to remove this heat. So at these time scales, thermal constants like kappa or the thermal resistances do not have much meaning, because those are quantities that are applicable in long time periods when all the optical and acoustic phonons can dissipate heat. Then we can see the effect of kappa or the thermal diffusion constant. But at short time scales, what you get is like nothing is dissipated. Nothing has time to move from where it's generated. So it will just heat up the device in a small volume. It is more like heat capacitance. Due to the heat capacitance, the device temperature is increasing in a very small volume. And once the temperature reaches a certain value, the lattice will dissociate, and that forms the craters that I showed before. It literally explodes and sublimes the lattice atoms along the track or where we have the most Joule heating. And it's related to, so how much Joule heating you'll get is related to, in some parts, impact ionization, because the original Neutron atom doesn't have enough energy to create enough electron hole pairs that can give rise to the failure rates we observe. So you need again to get the Joule heating we observe. So the gain comes from impact ionization. So in the blocking state, normally you don't have the impact ionization, but once you increase the current by creating electron hole pairs, you have the impact ionization happening at a lower voltage, and that can sustain a current for a long period of time and until the device fails or literally melts down along the track of the primary Neutron. So our initial analysis indicates that the Neutron is causing a Neutron or a recoil atom, primary or secondary Neutron. Then it creates electron hole pairs along a track. It's about 1 square microns in area and can be several microns in length. And that's in a large field. So then you have this J.E kind of heating, and that heating can be sustained for a long enough time, and that causes a failure. And that is, so when you calculate this failure, you shouldn't be using the kappas or the thermal resistances, because these are very short time scales, and they are generally governed by the heat capacity. So these are some of our initial calculations, and that this explains the same thing I talked before. So due to this sudden increase in heat in a very small volume or area causes the lattice to dissociate or fall apart. And so it can cause a sublimation or it can cause a material meltdown. And so here I show the sublimation in a very simple, using a lumped circle. Here I use the kappas, but these are actually applicable for very small volumes, not for the whole device. So you need to discretize the whole device into smaller volumes to be able to use kappa if you want to use it. Okay. So in summary, you have neutron-induced knock-ons causing current flow in a high field, and you have J.E type of heating in a very small volume, leading to a failure. But to conclude the talk, we went over what's causing terrestrial neutrons. So there are no neutrons in space. They are caused by high-energy protons hitting gases in the atmosphere, and that causes a shower of events. And since neutrons don't have charge, they can travel down to the sea level. And there are appreciable number of neutrons at sea level that can cause the power switch to fail. And in the case of, these neutrons cause failures in silicon devices and silicon carbide power devices as well. And in silicon, this is one of the most important reliability concern when silicon power switch or any silicon device is used in an application where you need a lot of these devices. So it's a matter of how many of these deployed. And at high voltages, close to the rated voltage, if you compare a similar silicon and silicon carbide device, silicon device tends to have a higher failure rate. But as you go down in bias, there's a crossover below which silicon carbide can have a higher rate. But at those levels, the failure rates are generally low. So for many applications, you may not need to worry about it. And to mitigate these effects, the circuit designers generally derate the parts. They use at a lower voltage so that the failure rates are suppressed. And our initial investigation shows these failures are due to impact ionization, so you need a gain factor causing fast temperature rise in a very small volume, and that leads to either sublimation or material meltdown. So, thank you very much. Hopefully this will help you.
Yeah, thank you very much, Akin. That was a very interesting presentation. You showed some really good data, and this is an important phenomena for folks who are doing product development or even research in silicon carbide devices. So very timely, and thanks very much for all the information.
Thank you.
We have time for a question and answer, everyone. So rather than everyone speaking at once, please use the chat box you'll find in the upper right-hand corner of your WebEx screen or WebEx drop-down menu, and type in your questions, and I'll read them out, and then Dr. Akturk will answer them. So we have one question already from one of the listeners. He asked, in slides 16 and 17, how are electron-hole pair generation events due to neutrons handled in TCAD?
Yes. What was the question? It's in TCAD?
Yeah, how are the electron-hole pair generation events handled in TCAD?
So in this TCAD, you actually get some kind of a failure rate estimation. So this is a post-process. So you don't resolve the actual mechanism of electrons and holes causing a failure. What you do is like, what we did was we found a field-dependent failure rate, but in a distributed form. So if you have a field-dependent failure rate, once you get the field profile of a device, you can run this like post-process and calculate failure as a function of position. Then you integrate it out to find the total failure as a function of area. So there are two levels of calculating the failure rate. One is just use a formula that's based on the field and run a post simulation, like post-process, to get the failure rate. Or you can do a detail. So this is at the first level where you have a field dependent failure rate, and after you get your regular field curves for a device in blocking state, you just run this post-process and it will tell you a failure rate as a function of position, which you can use you can integrate to get the failure rate for the device. I don't know. I hope this explains. This is what silicon people do too. They want to get some kind of a formula that's field dependent, so that when they design their hypothetical devices, they can do some kind of quick comparison of different device designs, so to find a device that is less prone to these kinds of effects. So that you can also do another ticket where you go to at the basics, like why this is happening. So this is at a higher level.
Thank you. I have another question. Is there a way to shield or protect the device from the neutrons that designers can employ?
There's no real any shielding methods. So the one bad thing about neutron radiation is it is very penetrating. So it can go through material without having any interaction. So that causes to penetrate long distances. That's one of the reasons neutrons can come down to the sea level, because they just go through the whole atmosphere. If you compress the atmosphere, it's equivalent to, I may be wrong, but it's about 10 or 12 feet of concrete. So they can travel the whole length of it. They may lose some of their energy, but they have enough energy to go through the whole thing. So there is no effective shielding to neutrons. And if you put lots of materials, high density material around your device, you can shift the spectrum to lower energies, but they'll still go through it. And it's also not practical to have enough shield to protect the device. You may need to put many meters of concrete around your circuit, which is not practical. So there's no real way to shield against this effect, so you all have to live with that.
Okay. Thank you. The next question is, you have a plot where you normalize SiC devices for area and rated voltage and plotted that against failure rate. Did you do something similar for silicon devices? If so, how does it compare?
So there's one curve, like if you look at the right curve, so this compares a silicon carbide power device with a silicon power IGBT. So that both are, let's assume their avalanche ratings are similar. So then, and the y-axis is sort of scaled by area, scaled by amp, which is kind of similar to area. So if you do that, then at the high voltages, silicon tends to have a higher failure rate. But at low voltages, most of the silicon devices can have like a lower failure rate. So you can get the curve similar to what I'm showing here, but maybe the slope of this curve is slightly different, where you have higher failures at higher biases and can have lower failures at lower biases. So the curves are still similar, but the slope of the curve is slightly different.
Okay, thank you. How do these neutron-induced failures, or the rate of these neutron-induced failures, compare to other potential failure mechanisms in silicon carbide devices, for example, due to material defects or other phenomena?
So there is not much direct correlation, when you have neutrons knock atoms off their sides, that doesn't always mean the device will be more leaky after that. I mean, the neutrons are kind of funny. So sometimes by irradiating a device with lots of neutrons, you may see a device characteristics improve. So that's kind of counterintuitive. So you can go either way. It's not always like due to neutron radiation you'll get worse effects. And if you have a material with lots of original lattice defects, actually with neutron, it may be more resilient to neutrons because of that, because whatever neutrons dislodging may not have that much of an effect because you have more of them already, if it makes sense. I think that is the case, for example, for some GaN devices. In GaN, especially in some GaN hands, you already have lots of defects. So if you dislodge stuff here and there, sometimes it doesn't matter. So they tend to be, it depends on which device you're testing, but they tend to be more resilient because they already have lots of defects. So there's no direct correlation, but having lots of defects in the material, which is not good for, I mean, you obviously don't want to have lots of defects because you can have a better device in terms of other reliability concerns. But if you have lots of defects in the material, you may have a more neutron hard device because the additional effects are not that important compared to your original. Yeah, and in silicon, you don't have, so you don't have, the material is so good, so neutrons have a much bigger role. So in especially in silicon microprocessors, I mean, the neutron reliability is like I believe it's the most important reliability concern.
Okay, interesting. Next question is, silicon doesn't perform well at higher voltages. That's part of the reason why we want to go to silicon carbide and GaN, et cetera. With that in mind, is the comparison to silicon devices fair above 600 volts?
So there's one comparison on the right here. So the question is should we compare them at lower bias? I didn't really get it.
I'll repeat it. Silicon doesn't perform well at higher voltages. With that in mind, is the comparison to silicon devices fair above 600 volts? You generally do this test at the higher bias, then you just extrapolate to lower bias. So for example, at the 1200 volt part, if you try to do the test at 600, it will take forever. I mean, you cannot really get the data. So the longer it takes to fail, you need to run the experiment longer. So for almost all experiments, that's not very practical to run anything at very low voltage. And in the case of silicon, at very low voltages, you cannot really make them fail because there's a very hard threshold. So for 1200 volt powers, you generally run the experiments down to maybe 800, maybe even lower. But the simulation experiment time is inversely proportional to the failure. So at some point, you just cannot run the experiment. So for 1200 volt part, you just don't try to do the experiment at 600 volts because it takes an extremely long time and you may not get any points. So if they are used at 600 volts and testing at the 1000, it may not look
too fair, but you can use that information to design a circuit for 600-volt application.
Thank you. And we have a comment related to the previous question, and the commenter says, regarding this question, there are silicon devices rated up to 4.5 kV, so we need to compare these parts. So that's not a question, just a comment. But I have a brief question.
I agree with that comment, by the way.
Okay. I have a question myself. You gave a back-of-the-envelope estimation of failures. You said an example, for example, if there were 10 million electric vehicles on the road, they each had about 20 silicon carbide devices in them, which is about what we've read that the new Tesla Model 3 has, that they would suffer approximately one failure in 10 years. I'm not an automotive guy, but is that considered a high failure rate for a discrete component in an automobile, or is that something that an auto manufacturer, would it give them pause?
I think it's on the edge. So I think for the as far as like microprocessors and other stuff is concerned, their failure rates, I believe, are lower. So
really?
they do not want anything like ever needs to be replaced, basically, obviously within practical time frames. So they do not make this car run forever, so it has some kind of limit. And so that limit, I believe, is, I'm not 100% sure, we need to check it, but I believe probably it's between 10 and 20 years.
Okay, thanks.
It also depends on like the cars. I mean, you don't use the car for long. I mean, the running time of a car is like no more than a few thousand hours, so
right.
that affects it too. But I'm talking about just the
lifetime,
calendar years.
Right, right. Because whether the car is running or not, it's still susceptible to these neutrons.
Yes and no. It is susceptible it is most susceptible when it is in blocking state. So
okay.
if the device is on, it is not that much susceptible.
Repeat that again. Say that again, please.
If the device is like in conducting state, it's on, then it is not susceptible. But if it's in blocking state, it is susceptible.
Okay. All right. Thank you for clarifying that. Well, we have time for one more question. If anyone else has any questions, please type them into the chat window. We have time for one quick question. Okay, if none, then thanks again very much, Akin. That was an excellent presentation, very informative. And I really appreciate your time and preparation, and thank you all for joining us again today.
All right, thank you all. And also, I'll send Rogelio a version of this slide so you guys can have a look at it and shoot me an email if you have any questions.
Do you have your email on the cover? Can you put that up again so people can see it, please?
Yeah. Actually, I also put this on every slide just in case somebody like.
Oh, okay. I see that. Great.
So, but you'll also, if you have the slides, you'll also see it there. So, like.
Great. All right. Yeah, that was very interesting. Thanks again, and have a wonderful day, everyone. And like I said, our next webinar will be on Wednesday, December 5th. With Ranbir Singh of Genesis.
All right. Thank you.
Thank you. Bye-bye.
Bye.